Industrial Application Society Student Branch, Chapter of SLTC Research University, in collaboration with the Robotic and Robot Division of Students for Exploration and Development of Space Chapter of SLTC Research University. I am 𝐿𝐿𝐿 and I will be joined by Netulya Suryaraj. Before we start off today's proceedings, we would like to provide all of you an insight of the two organizations bringing forth TechnoMind.
Thank you, Kavindu. Starting off, the IEEE Industry Application Society, IAS, is a chapter of the IEEE and is a world leader in the advancement of science and technology. The IAS provides a professional connection for the engineering needs in the industrial sector. IEEE Industry Application Society of SLTC Research University gives you the access to connect and collaborate with the professionals of the industry and to join with valuable national and international projects. SEDS SLTC is a group of highly motivated academics working to start further space exploration and development as a scientific discipline. SEDS SLTC promotes undergraduate students to investigate space by concentrating on the SEDS mission, which is bringing together students of many disciplines from all corners of the country to celebrate students' shared interest for all things concerning space. To be updated on the events organized by the IEEE IAS of SLTC Research University and SEDS SLTC, make sure to like the Facebook pages of both organizations.
Moving on with today's event, I would now like to invite the co-chairman of TechnoMind, Mr. Dilshan Agadawat, to address the gathering.
Good evening to you all. It's my pleasure to welcome you all to the workshop series of TechnoMind organized by the IEEE Industrial Application Society Student Branch Chapter of SLTC Research University in collaboration with the Robotics and Robot Division of the Student for the Exploration and the Development of Space Chapter of SLTC Research University. First of all, I would like to apologize for not turning on my camera since there's a power cut going on in our area. So let's carry on. The technological era has aided robotics and is becoming a rapidly growing area of various industries, including automation, agriculture, healthcare, and even space exploration. Owing to the lack of awareness of the robotics industry, the creative minds of Sri Lanka are stripped of the opportunities of progressing in the field of innovation. As a result, TechnoMind is being organized to educate students and undergraduates the fundamentals of robotics to much more advanced knowledge. TechnoMind aims to build a platform on which young innovators would be inspired to bring about an advancement in innovation. So, TechnoMind will be held on 3 stages. First stage, workshop series for undergraduate. The second stage, workshop series for school students. And the third stage for competition and exhibition. We have 3 amazing guest speakers for our first phase. Professor Chandimal Jayawardena, Academic Advisor, Dean of Faculty of Computing of Sri Lanka Institute of Information Technology, Mr. 𝐌𝐞𝐞𝐿, Director of Engineering Services of Watkins Wellness, and Professor Huan Gopura, Head of Department of Medical Technology of University of Moratuwa. We will be covering the topics robotics control system, product designing, and biomedical engineering. I hope TechnoMind will be a great experience to all of you, and you will gain the maximum of the inspiring personalities joining with us. I would also like to invite all of you to the competition of TechnoMind which will be set to be held on 12th of February 2023. More details will follow on the competition, so make sure to stay in touch with us. Finally, I would like to thank you all for joining with us and wish all of you very best. Let's carry on. Mal.
Okay, thank you, Dilshan. Before we move further, I would like to explain to you the workshop. We'll be hosting a live Q&A session to answer all of your questions. So please make sure to drop in all your questions and comments through our Q&A platform, the Pigeonhole, throughout the workshop. You will find the link in the chat box below. I would also encourage our participants to vote on any question which might be of interest to you, so we can provide a higher priority to them. Due to the time constraints of today's event, I'd like to apologize ahead of time of not being able to entertain all of your questions.
Now it's time for the most awaited segment of today's workshop on robotic control systems. Before inviting our guest speaker to take over, I would like to provide a brief introduction on our speaker. He is an electronic and telecommunication engineering graduate from the University of Moratuwa and holds a PhD from Saga University, Japan. His research areas include robotics, intelligent systems, and Internet of Things. He has 20 years of experience in teaching, research, consultancy, program development, and management. As an academic and a researcher, he has worked for Unitec Institute of Technology and the University of Auckland, New Zealand. Currently, he serves as the Dean of the Faculty of Computing at SLIIT. He's a chartered engineer, a member of Institution of Engineers Sri Lanka, a member of Institute of Engineering and Technology, a senior member of Institute of Electrical and Electronic Engineers, a chartered information technology professional, and a fellow of the British Computing Society. We are honored to have such an inspiring individual kickstart TechnoMind. I now invite the guest speaker for today's workshop, Professor Chandima Jayawardena, to take over the session. Over to you, sir.
Thank you very much for that kind introduction. First of all, I would like to apologize for this picture. I too have a power cut in the area, but soon I will be changing to the presentation mode, so that should be fine, I suppose. So I would like to thank TechnoMind organizers for inviting me to this workshop to deliver a speech. And I hope the content might be useful to the participants. So let me switch on to the presentation mode. I would like to share the screen. Okay, right. I hope you can see my screen.
Yes, sir.
Is it visible? Yeah.
Yes, sir. It is.
Okay, right. Thank you very much. So in my presentation, I would like to focus some important points related to software development for robotics. So I hope that might be useful for your competition. And so I have organized the presentation covering some general areas, some useful areas for robot developers. And depending on what you actually need for the competition, we might be able to have further discussions future. Now, if we try to understand the robotics market today, the robotics market has been changing over last, say, 1 or 1.5 decades. Now, in the past, the robotics was mainly for the industry. there are robots called industrial robots, as you can see in the top right-hand figure. You can see some robo manipulators. So these types of robots are called industrial robots. However, in the last 1 to 2 decades, the robo market has been changing from industrial robotics towards service and professional robotics. Now, even in the industry, rather than purely using a robot to do an automated task, such as fixing a nut or something, more and more robotics work are done with the collaboration of humans. So this is important to understand because this requires certain changes to the way we develop software and also the way we architect robotic applications. So today, robotic applications are more complex because of this, because in any robot, we have to embed a large number of software components. For example, if you compare these two pictures, in the top one, the robot manipulator has to move its end effector, the end point, the tip of the manipulator to the right place and do some work. So that is, to do that, actually you have to write software and you have to use various control algorithms. That is required. But if you look at the second picture, that robot is doing something with a human. So that requires more sensors to understand the world around the robot. And also using these sensors, the robot has to understand the nature of the world surrounding the robot. So rather than merely doing something, the robot has to be an embedded agent in the world. That is a key difference from industrial robots to these other types of robots working with humans. These other types of robots have various names. Some robots are called service robots, some are entertainment robots, domestic robots, and so on. Even if you are developing a rover to do some work in the real world, that is different to do something in a factory. Still, the rover will have to roam around the real world. So the robot will have to be embedded with various sensors and it will have to understand what is happening in the world. Now, in the robotics market, today we have robots with different capabilities, different sizes, different form factors, and so on. Some are given here. Now, because of these different types of robots, and since the work expected from them is different, the software itself is complex naturally. So we have to find out various ways to develop software to control these robots. And I would like to share something that I quite often share in my lectures, a comparison. Now, this video is from 2005. It shows a robot developed at Waseda University. It is called Wabian version 2. Around this time, researchers were actively working on developing bipedal robots. Robots can walk using 2 legs. Now, this Wabian 2 was a great achievement. I hope you can see. Now, Wabian 2 was able to walk like this. Right? It was a great achievement in 2005, not very long ago. And then in 2013,
we have seen the latest generation.
I'm sure you have seen these robots. This is called Atlas. Now, when compared to the Wabian, now this robot is more dexterous. Now, it can walk, maintaining its balance on this uneven terrain. So this is an area with snow. To walk in a place like this is difficult even for a human. Right? But this robot is capable of doing that. That was in 2015. This was in 2013. Right? A remarkable achievement. And so this is not very recent. So there are more recent videos. Now, if you look at this one, now in 2005, these types of things were available only in movies. Now, today, we can do these things. Now, what is the reason behind that? Is it an advancement in robotics technology? Yes, it is an advancement in robotics technology, but it is not merely an advancement of the things like new algorithms, new models, and so on. So the main reason behind this is software and the processing power. In 2005, it was not possible to do this because the calculations required to do in order to maintain the balance was not possible using computers available at that time. But today, using same approaches, you can do more things because you have more processing power, you have better embedded systems, and so on. And the software development for robotics has been developed over the last 20 years by a great deal. So what I want to highlight is, in robotics, there is this core area of robotics where we learn about robotics theory, right? So that area has also developed, but more than that, the capabilities of robots have developed because of the advancements of computing power and software. That is basically the advancements in computer science and engineering domain. So therefore, this fusion between robotics and computer science and engineering is very important. Traditionally, robots were developed by electrical engineers. The programming was done using languages like C++, and the programming was heavily used in robotics. However, software engineering practices and various techniques used in computer science domain were not directly or heavily used in robotics domain. But today, these two fields are converging. There are new conferences and new journals to publish papers and discuss about software engineering for robotics. If we look at robots in 21st century, we can see this fusion. Today, computers are continuing to be humanized. Humanized in the sense more and more software applications are developed with the understanding of the real world. And we have cyber physical systems. Those are the physical systems attached to networks or the internet. So you know about Internet of Things as well, right? So that is the area where computers are trying to understand the real world and to act on the real world. On the other hand, the robotics community is trying to develop versatile computing machines with high social impact potential. That was the one I mentioned earlier. Today, the challenge for robotic researchers is to develop robots that can understand the society. That's why it says social impact. Even if you take a development like an automated car, it has a social impact. when you put an automated car onto the road, in addition to correctly moving it on the robo, it has to understand various other social rules. For example, it has to understand even about ethics. There's a big debate about automated robotic cars on roboethics. If I give an example, now if you are driving a car, if an accident is likely to happen, sometimes you have to make a quick decision. On one side of the road, if you see a child, and on the other side of the robo, if you see an animal, or maybe an elderly person, and you have only two choices. Either you turn towards the child or turn towards the other person. How do you take that decision? Currently, when humans are driving cars, they take quick decisions in such situations where you have a moral dilemma. But if you want to do the same using an algorithm, it becomes very difficult, even if the situation seems to be simple. How do you embed that into an algorithm? So that's why the social impact of robots is becoming important. Now, to do this successfully, the fusion between the software domain and the robotic domain has to happen. The barrier that restrains their fusion is mainly due to the complexity of the software, right? Because the software systems must be reliable, maintainable, intelligent, and safe. And more than that, sometimes it has to understand legal and ethical aspects as well. So therefore, the software development of robots have come to a state where you have to consider multiple aspects. So I wanted to highlight that at the beginning of the lecture, because ultimately you will be developing a software, and software for robots that is still complex as it was 30 years ago. Now, although the software development has developed, although it has come a long way, the software architectures for robots, so basically developing software for practical robots, is still complex. And this may not be very evident if you are developing a software for a very simple application like a hobby project. But if you want to develop a robot for a real task, usually you need multiple experts from different domains: electrical engineering, computer science, software engineering, and so on, machine learning. And developing the architecture of the software has to be well thought of. There are various techniques to do that today, but still in most projects, these things are not followed 100%. As a result, the software, the most software that we develop for robots are monolithic. I will further explain what is monolithic in later slides, and hardly adaptable to different situations, and hardly reusable for different tasks or for different robots. If you are developing software for a competition like this TechnoMind competition, still it is worth putting some thought to the architecture of the robot. How you want to control that, what kind of software architecture that you are going to use. That will help you quite a lot later to achieve the task that you have to complete. The current status of the Robo market is like this. We have heterogeneous robots, different robots with different capabilities, varying locomotion methods, sensors, actuators, and with different modes of interaction with users. locomotion method means the way that robot moves in the environment. Right? If you think of a rover, its locomotion method is different to a bipedal robot. Right? So therefore, one important thing is when you develop software for these different situations, some kind of reusability should be there. Otherwise, when we change the locomotion method or the robo basically, you will have to rewrite the entire software. So that has been one of the problems in the robotics market. So therefore, today there are certain techniques to reduce this overhead. Now, these are the challenges for software development for robotics. There are no or little standards, and the code reusability is very little. Now, when you develop software in other areas, for example, when you develop a software for commercial use for a business application, code reusability is one important aspect, because otherwise, when you develop different types of applications, every time you will have to write everything from the scratch. But in robotics, so therefore there are techniques. So you have heard of, I mean, people do version controlling, and the people try to reuse their code. But in software domain, this is very this is happening at a lower level when compared to other areas. So therefore, you will have to rewrite code for most common tasks. And it is not only about rewriting, it is related to testing as well. You have to architecture your software in a way that you can easily test it. I will explain it a little further in a later slide. Now, up to now, I was talking about general challenges and some important areas of software development for robots. Now, then I want to move on to controlling a robot, because that is something directly relevant to your competition. Now, before start writing your software, as I mentioned earlier, put some thought to the architecture. Now, this is how we control a robot generally. Okay? This is not the only way to control a robot, but generally this is how it goes. Now, this kind of approach is required if you want the robot to do some precise task. For example, if you want the robot to move from point A to point B following a particular path, you will have to do something like this. Now, here you can see the real world environment. Real world environment is where the robot is operating. It can be a building, or it can be outside, underwater, some real world environment. Now, if you just want to move the robot randomly, you don't have to do much. On the other hand, if you want to remote control the robot, again, you don't have to do much. Here I am talking about an autonomous robot. An autonomous robot should be able to move or do something by itself. To do that, first of all, it has to understand the real world. For that, it needs perception. How do we get perception? Perception is achieved through sensors. Now, as an example, I will take a simple example of going from point A to point B following a path, say a road. Then the robot has to detect the road, detect the path, and also it has to detect the surrounding obstacles to avoid collisions. That is basically understanding the real world. So that is done by taking various measurements using sensors. These sensors can be cameras or other types of sensors such as laser range finders, sonar sensors, and so on. And after that, it has to do what is known as localization. Some of you may have learned these things in university. Localization is finding one's own position with reference to the environment. Now, for example, if someone take us blindfolded to a building and put us somewhere, or let's assume someone takes you blindfolded and put you in a place in your university, and then you remove the cover, and by looking around, you have to understand your location. Because without understanding your location, you can't do anything. You can't go anywhere. How do you do that? To do the localization, as a human, what you do is you look around. If you see a familiar object or familiar place, then you can refer that the detected or seen object with the map in your memory. Then you understand, okay, I am in University of Peradeniya. Now I am in front of the Senate building, something like that. Or if you are in SLTC campus, if you see a big satellite dish, then you will understand, okay, I am in SLTC campus. I am in front of this building. Something like that is localization. A robot will have to do the same thing. For a robot, this is harder than a human. There are various algorithms to do that. So depending on the task you have to do, you have to plan how to do this localization. After that, now robot knows its current position. Now, to do something in the environment, it has to plan what to do. For example, from your current location, you have to go to a different location. To do that, you have to plan your path. For that, you have to have some intelligence. For a robot, you have to give some intelligence. This can be done using various techniques, AI techniques. You can use some algorithms. So that step is cognition. After that, you have the path. Now, currently you are in a place, you have identified, you have localized that you are in point A. Now you want to go to point B. Now you know how to go there. And then comes motion control. Motion control directly refers to moving the robot in the environment. Now, if you have a robot with, say, 4 wheels, and out of these 4 wheels, 2 wheels are motorized. You have motors connected to 2 wheels. Then the only way to move the robot in the environment is to rotate these motors. Right? When you are rotating these motors, you have to calculate how much the rotation should be. Right? And then you have to precisely control those motors by that amount. Or if it is a different type of robot, it is still the same. Whatever the motion control method, you will have to do it. Right? So once the motion control is executed, the robot will move in the environment, right, to a different place. So it will slightly move in the environment. And then this cycle continues. Now, this is the classical way of controlling a robot. Right? If you want your robot to do something very precisely, still this is possible. Right? Although there are alternations to this one, we have to understand that this is the fundamental way that a robot works. Right? Now, that means basically you have to implement these 4 components in your software. In addition to that, you have to have some kind of map or a representation of the world in the robot. If it is a building, sometimes you can build a map in advance and give it to the robot. There are techniques to do that. Sometimes, if you don't have a map, there are techniques where a robot can build its own map and use it. Right? So these things are required to do if you want the robot to do something in the environment. Now, let's try to understand some approaches to do this one. Now, here, the localization step can be quite difficult because it is highly error prone. Right? I am not going to discuss that in detail, thinking of the limitation of time, but you have to understand that it is very serious in a robot where you want to move it in the environment, because without doing localization, you can't move it to the precise location, right? And the limitations of sensors, such as sensor noise, sensor aliasing, and also effector noise, and errors in position estimation, all these things affect the localization. But there are techniques to overcome those things. You have to understand those techniques and use it in your project. Now, to give you an example, if you think of a robot moving in a straight line, right? You can calculate the position of the robot using odometry data. That means if you know that the amount of rotation of your wheels, because you give commands to rotate the wheels, right? So if you integrate all those small movements, you can calculate the current location of the robot. This is known as dead reckoning, right? Now, but uncertainty of robot's position grows. Now, in this graph, this circle represents the uncertainty. That means now the robot starts at point 0. When it is 0.25 away from that point, the calculated position is this one. Still, it is fairly accurate, right? So you want to move the robot in a straight line. Now, but when the robot is, say, 1 meter away from that point, you are not sure whether the robot is exactly on the straight line. Instead of that, what you can say is the robot is somewhere within this elliptical area. That is uncertain. So this uncertainty grows with the distance, right? So this affects the localization. So therefore, for localization, you have to use multiple techniques. The sensors on the robot itself is not sufficient. If you use robots on the sensors itself, sensors on the robots itself, you will get a situation like this. And using those sensors, you have to detect some external factors, things something like a landmark or something, and correct your position. And when the robot is turning, again, there are uncertainties like this. Right? We have to know these things before we determine how we want to do the localization. That's what I wanted to highlight. So there are techniques to reduce this type of errors. Now, because of that one, suppose in your project, you have been asked to, I don't know the task of your competition, but suppose you have to start your rover in one point, at one point, and move around a square and come back to the same point. It appears to be a simple task, isn't it? But when you come back, quite often you will be in a different point like this. So in the diagram, you see the starting point, and you calculate and move, say, 10 meters forward and turn 90 degrees and 10 meters. So likewise. So theoretically, you should come back to the same position. But what happens is, look at the right-hand side figure. When you move forward, you think that you are moving the robot in a straight line. But in fact, it is not moving in a straight line. It is slightly drifting. Right? This red line, this dotted red line is the actual path. And then you turn the robot in the clockwise direction by 90 degrees. But once again, the actual rotation is 87 degrees. And you can understand the rest. As a result, finally, the robot doesn't come back to the required position. And also, it is not exactly in the required orientation. Right? So, correcting this can be quite hard. You have to think about these ones and use suitable techniques rather than directly trying to control, directly trying to, start writing programs. And sometimes, depending on the task, you don't have to do exact planning. Now, in this case, we are trying to move the robot around a square. But sometimes the task may not require that. For example, if the robot is at point A in this building, and if it is supposed to go to B, right? If that is the task, and if you have the freedom to use different techniques to achieve this task, then there are other robust methods. Because to move from A to B, there are multiple paths, right? The one approach is to go out of, I think you can see my mouse pointer, you can go out of this door and go along the corridor and come to B. That's how a human might walk. On the other hand, a robot can simply follow one of the walls and eventually come to point B. Right? So that might take a longer time, but still the task may be achievable. So you have to understand the task carefully and see whether it requires precise control or whether you can achieve it in a different way. And to control a robot, there are two main approaches. I will briefly explain those two, thinking that might be useful for your work. One is called model-based navigation. That is the one I explained a little earlier. We take inputs from sensors and perception, localization, cognition, and motion control, step by step. Right? So this is called model-based navigation, and this approach is suitable for certain tasks, depending on the task. The other one is called behavior-based navigation. Here, now one central control loop is not there. Now, in the previous one, we start from perception, localization, cognition, motion control, and then go back to perception. So this is a loop. In this one, instead of implementing your software like that, you implement several independent behaviors. We call them behaviors because this architecture was inspired from animal behavior. Now, in this case, these are some examples. A robot may have a behavior to follow a wall. And completely independent from that, it may have a behavior to avoid obstacles, detect goal position, discover new area, communicate data. Now, these things are implemented as different software components. They work independently. The following the wall is completely independent from avoiding obstacles. The final observable behavior of the robot is the sum of all these behaviors. We say the robot has an emergent behavior because finally, if you observe the robot, it will display a combination of these. So this architecture is quite powerful because using this kind of architecture, you can achieve certain things that cannot be done using the previous architecture, this one. However, the previous one, the model-based navigation, is still powerful for certain tasks. So you have to understand the task first and then decide what approach to take. Up to this point, are we taking questions? Is there anything? We'll continue so we can discuss at the end. Right? Sorry. Now, in the model-based navigation, now that is known as hierarchical paradigm. If you want to use that kind of approach, you have to have a control loop for the robot. Right? It is the main control thread of the robot. So you take inputs from sensors and process the sensor data, things like extracting features from camera data or laser range finder data, and then using the model that you have. Model is something like a map, right? You plan the task after doing the localization and then do motion control. This continues, right? So this is called horizontal decomposition because tasks of the robot are horizontally decomposed. We can view it one after the other, right, as series of tasks. The other one looks like this. It is vertical. So this is more biological because, as I mentioned, this was inspired from the biological world because if you think of an animal, if you think of us, we can do multiple things independent. For example, we can drive a car while listening to a song. Listening to the song is independent from driving the car, isn't it? So listening to the song is one of these behaviors. And driving is one behavior. And thinking about something is another behavior. Or you might do eating at the same time. Those are different behaviors. So the observable behavior is a person is driving a car, eating a banana and listening to a song, something like that. Similarly, you can develop a robot with the required behaviors. Avoid collision can be one behavior, wandering another behavior, exploring another behavior, building maps another behavior. The combination is the ultimate outcome, right? Using this approach, sometimes you can develop full robotic applications with less complex software. And I will explain you now. Now, although I explain you might be wondering how to do this. I will explain you one architecture called Subsumption Architecture, which can be used to implement a behavior-based robotic system, right? Now, in the Subsumption Architecture, it is very similar to it is actually a behavior-based model. Only thing is here, it is the first two, what I explained, these two are two paradigms or two approaches, right? this is a particular architecture. Sorry, subsumption architecture is a particular architecture that you can use directly to implement this one. Now let's look at that briefly. Now you can here this is an example of developing a robot that can move in the environment and do something, right? Now let's look at one of the behaviors that you can implement. Now this behavior is called avoid behavior in this example. In this one, a robot capable of moving forward while not colliding with anything could be represented with a single layer, level 0. Now look at this one. From sonar sensors, you get the polar plot. That is, if you have sonar sensors around the robot, you will get different readings from these sonar sensors. From that, you can develop a polar plot. And from that polar plot, you can determine if the robot is going to collide with something. And if that is the case, you can stop, right? And that is represented by this bottom one. The first step calculates whether the robot is going to collide using sonar sensor data, and then you send a stop signal to the motion control unit of the robot, right? To make it more clearer, if your robot has 2 motors, and if those 2 motors are controlled by a Raspberry Pi board, you will send this control signal to that board to stop the motors, something like that. And then so I have actually excluded some of the details to reduce the time. This field force, this component, this step calculates basically tries to move the robot away from obstacles. If an obstacle is closer to the robot, this will calculate a heading, the heading direction of the robot to move it away from the obstacle. So that heading will go to the turning module of the robot. So ultimately what happens is the robot will move away from obstacles, and if it is going to collide with something, it will stop. So that is the first step. Once you have implemented this, now if you think carefully, if the robot is stationary somewhere without any obstacle around it, robot will not move anywhere. But if you bring an obstacle closer to the robot, or if someone comes closer to the robot, it will feel a force. On the other hand, it will detect that obstacle is closer to the robot, and robot will try to move away from that. Right? So that is the level 0 behavior. And then I will not explain these details. Now, okay, now this is level 0. You get sonar inputs and it will move forward and move away from obstacles. And then let's try to introduce another behavior, wandering behavior. In level 0, in the first behavior, the robot moves away from obstacles, but it is not moving in any particular direction. If you want the robot to randomly wander, you can implement it as another behavior. This wandering module can generate a random heading, right? And you can give that random heading to the robot. This S stands for subsumption. It basically overrides the previous heading. The previous heading or level, the heading generated by level 0 behavior is to move the robot away from an obstacle. Now, in addition to that, this wandering behavior is calculating another heading to wander. Now, if you have both these behaviors running, the robot will wander in the environment. At the same time, it will try to be away from obstacles. Now, let's see what happens when we have a third behavior. Third behavior can be follow corridors. Now, in the third behavior, using same sonar data, this third behavior tries to identify corridors. If a corridor is identified, then a heading is recalculated to be in the middle of the corridor. So it overrides the previous heading. Now, when all these three behaviors are running, what we observe is the robot is wandering, and if it comes closer to an obstacle, it will move away, and if it detects a corridor, it will go through the corridor. Now, it is quite powerful behavior when we have all these three running. Now, in software, these three are independent. These are usually implemented as three independent software components. So therefore, if one stops working, still others will be running, right? So you can do some more readings on the subsumption architecture. You will find plenty of examples. Now, this is the final diagram when you have three behaviors. Now, if you think of a situation like where you have a rover, so you are supposed to maintain the height of this rover at, say, 1 meter from the ground, and you are supposed to move in a maze, and if you detect a particular object, you are supposed to stop. Say you have to do that, right? Now, these three can be implemented as three behaviors. One behavior is to maintain the height of the rover at 1 meter from the ground. It is independent from the other. And the second behavior can be to move the rover in the maze. And third behavior is to detect that particular object that you are supposed to detect. Something like that, right? So when you implement these as different behaviors, there are multiple advantages in terms of software, because you can implement these things as independent software components. You can test them separately. You can make sure that one behavior is working properly. Otherwise, if you build the whole thing as a single monolithic system, testing and debugging will be quite hard. So therefore, in real software projects, usually different behaviors are implemented as different software components. Now with that, we come to component-based robotics. Right? Component-based robotics is where you implement different functions of the robot as different components. If you decide to use a behavior-based architecture, as I explained earlier, naturally this becomes the suitable software architecture, because you can, now these boxes in this figure are different software components, independently running software, different pieces of software. If you use a behavior-based architecture, you can have one of these boxes per behavior, right? But component-based robotics is not only limited to that one, only limited to behavior-based architectures. Even if you don't use a behavior-based architecture, still this is useful. Now here I have shown the architecture of one of the projects that we completed some time ago. It was a robotic wheelchair, and this wheelchair was capable of detecting speech and generating speech, and detecting gestures, detecting face, and measuring blood pressure, and so on, doing several things, different things. Now, these things were implemented as different components. When we, a component is an independent piece of software. So when we do that, there should be a way to communicate between these different components, right? To do that, you need what is known as a middleware, right? Middleware, without a middleware, actually it is very difficult to develop a reasonably complex software. Now, this is a different robot. Again, one of the robots that we developed some time ago. This robot was for elderly care. So this robot had a camera and touch screen and several sensors. And a robot like this can easily have tens of hundreds of different independent software components running on it. Now, if we try to develop the whole robotic application as a single piece of software, you cannot handle the complexity. So therefore, the different tasks are divided into smaller pieces, and those smaller pieces are implemented using components. The advantage is you can use different programming languages if you need for different components. And some of these components may be readily available. For example, if you want to do TTS, text-to-speech, today you don't have to write it from the scratch. There are text-to-speech engines. You can use one of those engines, right? Similarly for face recognition, right? So you can use readily available components. And only thing is you have to use a middleware and communicate between these components. Now, there have been many different types of middleware in the robotics industry. Player was one of the early middleware, especially used in research and education. And OpenRTM is a middleware popularly used in Japan. And Opros is a middleware used in Korea mainly. So likewise, there have been many middleware types. Even Microsoft Robotics Studio can act as a middleware. But today, I am sure most of you have heard of ROS, Robo Operating System. Robo Operating System has converged some of these middleware types into a single project. Today, almost all research robots and most commercial robots are compatible with ROS. So therefore, I highly recommend you to use ROS for your project. It will be the development will be quite straightforward, not really straightforward. It will be easier than not using it. There are plenty of places to get help with ROS. So ROS started in 2007 and at Stanford AI Lab, and since 2014 it is managed by Open Source Robotic Foundation, and it is a community-based project, an open source project where independent developers contribute their software and create various distributions. And the advantages are the ROS is a peer-to-peer architecture, and it supports distributed architectures. You can run some of the components in one computer and some others in a different computer. In fact, you can have any number of computers. Some of these computers can be embedded devices, some can be PCs, and so on. You can use multiple languages. It's lightweight, open source. So therefore, it is quite powerful. Now, it supports hardware abstraction for lower-level device control. So you know the meaning of hardware abstraction when it comes to computers. Now, because of the operating system, now we don't have to think of hardware devices when we write a program. Similarly, when we use ROS, low-level devices can be directly controlled. For example, if you have a camera or a laser range finder on the robo, you can use readily available components to get inputs of these devices without thinking of the actual implementation of the device driver. Right? So that can be done easily. And for most commonly used functions, open source components are available. And it supports message passing, and it has other software, useful software related things such as package management. So therefore, it's quite powerful. You can go to the ROS wiki, wiki.ros.org, and so there are plenty of tutorials. You can easily self-learn from that and use it for your project. And now this is the basic architecture of ROS. It has a concept called a node. Node is a running software. And nodes, for example, the camera module can be one node. And your face detection module can be another node. The camera module takes the physical camera is connected to the camera module. Camera module is the software module talking to the camera. And that camera module, that node, takes images and it can publish these images to a topic. The topic is like a pipeline, right? And another node, if you have a separate node for face detection, that face detection node can subscribe to that topic and take images. So these two nodes run completely independently. If one goes down, nothing happens to the other module. This communication happens through the middleware. And in addition to the face detection module, suppose another module requires images coming from the camera, say obstacle avoidance module. So one module is for face detection, the other module is for obstacle avoidance. Both nodes use camera images, but you can have only one camera module. Only thing you have to do is both those nodes have to subscribe to the same topic, right? So by doing that, you can have a loosely coupled architecture like this one. This distributed middleware, the green one, is like a bus where independent components can publish to and subscribe. Right? By publishing and subscribing, these nodes can communicate with each other. There are few things more than subscribing and publishing, but so you can probably study those things later. I just wanted to point you to useful locations where you might be able to start. And another important and useful thing is, with ROS comes a simulator. I highly recommend you to use this one. This is called 𝐿𝐳𝐵O. 𝐿𝐳𝐵O is a simulator, but it is a dynamic simulator. You can create a dynamic model of your robo and simulate it on 𝐿𝐳𝐵O. For most available robots, these models are available. Now, for example, this shows a PR2 robo. The PR2 is a popular research robo. The model for PR2 is available. So you can download it. And if you have a real PR2 robo in your lab, doing something on real PR2 may be somewhat difficult straight away because you will have to deal with hardware complexities. So if you want to quickly test something, you can write your software and test it on the simulator first and then put it onto the robot. The robot and the simulator works in the same way. On the right hand side, you see a turtlebot robot. This is again a robot used for teaching mainly. If you want to do something on a robot like this, first you can use gazebo and do your first basic testing and then use the actual robot. Even for your rover, you can do the same. Right? I highly recommend you to do this one because by using gazebo, you can first test most of your algorithms. And before you actually put it onto the real world, and by doing that, you can save a lot of time by correcting your software. And again, there's another one called RViz. This is a visualization environment that works with crossing. Using RViz, you can get the view of the robot. Now, on the left-hand side, you see a robot, right? Robot in a human space. This robot has a laser rangefinder. And on the right-hand side, you see what the robot sees. In other words, the right-hand view comes from robot's laser rangefinder. This is very powerful for debugging, right? So you can easily understand the robot's view of the world. So using gazebo and RViz, you can they help you to fine-tune your algorithms and test your algorithms. And this again, another thing is this gazebo, RViz, and your actual robot control software, they can run on different computers. So by doing that, you can these things can be monitored by multiple people, and you can easily use computational power on other computers. So I recommend you to use this as well. Then there are various tools coming with ROS, where you can visualize how your software is interconnected, how your nodes communicate with each other. You can use those to easily debug your software. Now, those are the things I wanted to discuss in today's presentation. The time is already finished. So therefore, I would like to stop at this point and answer if you have any questions. And depending on the actual task of TechnoMind, sometimes you might have to do different things. So if anyone needs help, we can have a further discussion later. So if we have, I am still in the dark, but if you have any questions, we can have some.
Yes, sir. Thank you very much, sir, for sharing your knowledge and experience with us. So there are some questions asked from us. So the first question is, without the development boards, are there any simulators for us to learn about codes? Shall I repeat it?
Okay, yeah.
Without development boards, are there any simulators for us to learn about the codes?
Now, now there are multiple answers to that. I mean, as you know, if someone is asking, there are various, coding. If someone just wants to learn coding, there are plenty of places like, for example, REPL. But I think here you are specifically asking about robots, right? So since you are asking about robots, what I recommend is Gazebo. That is actually, but in addition to Gazebo, there are other ones like VREP, for example, right? VREP is a good simulator that we use for teaching. On that also, you can have various models of robots, and you can write software to control robots. But the gazebo with ROS can be recommended for this task because then you can write your actual software. What do I mean by the actual software? Now, if you have a robot, a physical robot, you can have the same model, exactly same model on gazebo. So therefore, you can write your software in, say, in C++, right? You can write it on a computer. You don't need a development board, and then you can execute it on gazebo, right? And if it is working, then you can put it on the robot. Now, if I showed you that turtle bot, for example, that turtle bot runs using a Raspberry Pi, right? So so if you use the real robot, you have to develop the software on Raspberry Pi and execute it, right? Instead of doing that, you can you can write your software and run it as a node on your computer, on any kind of PC, and execute it on gazebo and see whether the robot is working well. And after that, you can actually execute it on the robot. So I can recommend that, thinking of the tasks that you are going to do. You don't need development boards if you do that. Actually, that's why we have those simulators. Any other question?
Thank you so much for that answer, sir. Yes, we have some other questions as well. So the second question is, so what is the most suitable and reliable option for mapping indoor environment for mobile cargo robots?
Now, that is for mapping. You can use now the currently most widely used algorithm is called SLAM, simultaneous localization and mapping, and there are various extensions to that. And once again, now you don't have to write these algorithms from the scratch because those modules are available. If you install a Robo operating system or ROSN, it has a navigation stack. It is called the navigation stack. As a part of that, this mapping, indoor mapping module is there. So that is the most fast. These indoor mapping modules are based on the SLAM algorithms, various SLAM algorithms. So you can use one of those and test your robot within a short period of time. That is the most reliable method, thinking practically. And if someone wants to learn, study, then you can start writing your own algorithm. You can write your own SLAM algorithm. That type of work is done in some research, right? But if your purpose is to build a robot and do something, you can straight away use the ROS navigation stack and use it.
Okay, so thank you for the answer. So they have asked, are there any other free simulators like Gazebo to design and simulate robots? Are
there are other ones, right? Something we commonly use for teaching is VREP. I mentioned that VREP, and another one is this Microsoft Robotics Studio. Using VREP is easier. VREP is easier just for learning. If your objective is mainly teaching and learning, that is easier. But here in this case, your objective is to build an actual robot. In that case, I believe that Gazebo is better because when you use the Gazebo, you can keep your software separately, as I explained earlier. So you can write your software, test it on Gazebo, and then put it on the robot without any major modification to the software. So therefore, although other simulators like VREP, Microsoft Robotics Studio, and so on, the ROS and Gazebo may be the ideal for this task, for your competition, I believe. That is more general, and it is more flexible than the other ones that I know.
Okay, sir. Yes, the next question that we have for you is what is simultaneous localization and mapping? And what are the practical applications of that?
Yeah, no, it's a good question. Now, as I explained at the beginning of the presentation, to move a robot in a given environment, we have to do localization. That is basically the robot has to understand its current location, right? This has to happen continuously when you move through the building. You start from point A and you understand your current location, localize, and say move 1 meter. And after that, the same thing has to happen again. So otherwise, robot will lose its knowledge about the position, or it will not localize, so it will not be able to move to the end. Now, to do this, one approach is to have a map, right? A priori map, a map built in advance. That is used in some applications. If it is a building, there are various different types of maps. You can use topological maps, logical maps, and so on. You can build a map and put it on the robot. And using that map, robot can move. That is one approach. But one problem that robotic researchers were working in the past was to do this without having a map. Now, if as humans, now when we go to a place, we don't have a map, right? We move around a building and we build an understanding of the location, and after that we can move, right? So effectively, humans, we do localization and mapping simultaneously. So if you are in a new building, while you are moving through the building, you remember some of the features of the environment. That is mapping, right? And at the same time, if you come back to the same location, you understand, okay, now I was in that location 1 minute ago, now I am in the same location. You can do that. Now, if robots can do the same thing, that is very powerful, because then robots can go to new environments. So therefore, there is a mathematical algorithm where a robot can do the map building and localization at the same time in unknown environments using certain features of the environment, right? So there are variations to these algorithms. There are a number of slightly different SLAM algorithms. Basically, the meaning of SLAM is doing localization and mapping at the same time in an unknown environment, right? As I mentioned earlier, you don't have to write your algorithms from the scratch. To learn how it happens, you can use one of the existing algorithms first and put it on the robot and see whether you can use it. Normally, what you do is, once you implemented your SLAM algorithm in software, first you move the robot in the environment, right? Say randomly. So then by doing that, robot can collect environmental features and build the map. And after that, if you ask the robot to move from one place to another, it can move, right? It is a good alternative to building a priori map.
Okay, sir. Thank you for your answer. So the next question is, what are the best microcontrollers or suitable controller for robot if they are going to use the system like ROS, which can run many threads at one time?
Which can run many threads at
one time.
Now, for that, basically, now you can, there's nothing called best microcontrollers. Now, since you are going to build this in the country, basically you can use whatever available, right? Now, today, in what in most projects, in research projects, you can use boards like Raspberry Pi, right? Now, they all support this ROS. Even now, for simple applications, you can, not in simple applications, sometimes in the same robo, you may need multiple boards. Now, suppose you have some motors and your logic on the robo, and to control the motors, you will have to generate PWM, for example, right? PWM signals to control speeds of motors. For that, sometimes you will have to use a simpler microcontroller board like an Arduino, an inexpensive one, right? Just as an example, right? So that can be dedicated only to generate PWM signals. And to do your higher order work, like processing images, you can use something like a Raspberry Pi board, right? And if you need more than one board, you can have all those. And if you have other things like if you want to access a database and get the face of a person and identify that, you can even use the PC in a different location, the server. Now, all these things can be connected using ROS. The Arduino, if you don't have an external thing, you may have a couple of Raspberry Pi boards and then Arduino. All these can be connected using ROS, and you can run different nodes on these different boards. If it is a simple one like an Arduino, you will run only one node there. But on more advanced boards, you can run multiple threads. So therefore, basically, you can use whatever you can purchase for a reasonable price. And so you don't have a big restriction these days. Now, natural selection would be Raspberry Pi, thinking of the availability, but I think they are also expensive and sometimes difficult to buy in the country these days.
Okay, sir. Now we shall move on to our next question. Which type of development boards are the most suitable for robot control systems?
Development, I think it's the same thing, isn't it? The answer is the same, I think. Development boards, if you are the same types of embedded boards can be used. For small robots, it's mainly Raspberry Pi, that type of boards, ARM processor type boards. I think answer those, it's the same, basically same answer.
Yes, the next question is, what is the difference between ROS and ROS2? So can you explain?
In ROS, that is the main differences are, there are a number of differences. Okay, I have power. Give me a second. Now, there are certain areas, for example, there's something called parameter server in ROS, and it is implemented differently in ROS2. And the way the packages are organized is different. But when it comes to the basic way the ROS works, it is not actually different. The way packages are organized, how packages are created, and how parameters are saved, and also the ROS core, the central part of the ROS operating system, how it is structured. Those things are different, but when it comes to the basic functionality, it remains the same. And some packages are not compatible. So therefore, if you because still now in ROS, what happens is these packages are contributed by volunteers. So therefore, even between cross distributions, when you have a new cross distribution, some packages become incompatible for a certain time until you make some changes. So therefore, it might be good if you use ROS, because you can have more choices. You will, the most things are available still in ROS. ROS 2, if you want to try out ROS 2, that is also fine. The main difference is in the architecture, not in the functionality. Anything else?
No, sir. Sir, we have reached the end of the Q&A session. So thank you, sir, for answering all the questions. And thank you very much for your curiosity and sending so many questions. And also due to the time constraint we have in the event, we have to bring this session to an end. So Natulya.
Yes. I believe today was a memorable day and an immense success. Yes, Kamidu. A huge thank you goes out to our guest speaker, Professor Chandimal Jayawardena, for taking time out of his busy schedule and gracing us with his presence here today. Thank you. Sir, to show our appreciation for the support and dedication you have shown to make today's session a success, the organizing committee of TechnoMind would like to issue a virtual token of appreciation. Thank you very much, sir. In order to remember this moment in the future, we have a special request from our participants. Please switch on your cameras and join us for a photograph.
And thank you very much for your token of appreciation. I highly appreciate it.
Yes, sir. Yes. I would like to request our participants to switch on their cameras and join us for a group photograph. Yes, thank you. I would like to move over to and give over to Kavindu.
Yes, Natulya, thank you. Next, in the next week, on 17th of December, we have the second workshop of TechnoMind, which will be discussing on the topic of product designing. We will be having a very special guest with us, Mr. 𝐷𝐼𝐿𝐼𝐿 Gunawardhan, Director of Engineering Services at Watkins Wellness. We would like to remind you to fill the feedback form so you could ensure a valuable certificate for joining our workshop series. Finally, on behalf of the IEEE Industry Application Society Student Branch Chapter of SLTC Research University and the Robot Division of SLTC Student Exploration and Development of Space Chapter of SLTC Research University, I would like to thank you all for joining in with us today. We hope you found this workshop very useful. Thank you very much. I'm 𝐿𝐻𝐵𝐻𝐿 and wish you a very good night.
And I'm Natulya Suryarachi, signing off until we meet next time. Stay home and stay safe. Thank you.